So one of the things I want to start with, though, is you're hearing a lot of talk about the equipment. I'm going to get into that. I'm going to get into sizing, design for homes, how to meet the range of the load that is necessary. But one of the things that we see as HERS raters that's really important, it's really the communication. It's really the management of the job. It's so important to be able to communicate well with the architect, with the site manager, and with anyone who's involved in the project. The HVAC contractor, typically, particularly on production jobs, but on many jobs for new home construction, there's traditionally very, I would say, not great communication between the tradesmen. So you've got your electrician, you've got your HVAC contractor, you've got your insulation company, and they all come in. Sometimes they work well together, other times they're just pushing each other out of the way, everybody just doing their own thing with their heads down. So what we sort of bring to the table is this perspective of looking at the whole, not just coming in as an HVAC contractor, designing a system to meet a load. We're looking at the house as a system, the whole system. But we're also, really putting forth an effort up front to try to engage all the stakeholders, right? The stakeholders may be the architect. Many times it's the architect. We'll get on the phone, we'll go over the design, we'll go to a conference room, we'll go over it, find out what the we want the builder's input. We want to know what they have in mind. When we get down to details like mud rooms and bathrooms and how we're going to approach it. And sometimes we're on the phone or we're meeting with homeowners who are going to be living in the home. So it's really important to get their input and to coordinate the whole thing. So you're not just a bunch of different specialized contractors going in doing your thing and you end up with what you end up with. I cannot stress the management, the project management is just so important. And so we try to bring that to the table, do as much of the thinking up front, and really create a project that's successful in terms of energy efficiency, but also successful in terms of comfort in every part of the home. So we're going to start with some design considerations, the importance of testing verification, accurate system sizing, design layout recommendations for new construction, and then we've got some case studies. So considerations that impact, these are sort of bigger picture kind of considerations when you're looking at a house and getting ready to design. Again, usually we're working from plans. So we have plans. First we do, of course, the manual J. So we do that ourselves. And then we plug in those loads by room, and then we start matching the equipment, and then we start thinking about distribution. But a home, you really need to understand, you're going to want to talk about this today, all the building science, right? And, the various forces on a home, the convective forces in the winter have to do with temperature, and so forth and so on. But it is not just doing the load counts and putting a system in a house. It's really looking at the true R values of a home, what the air leakage rate is going to be, what the ventilation is going to be. All of those things are incredibly important. And it's also really good, anyone who's a HERS rater in the building science stuff understands the principles of heat transfer, conductive, convective, and radiant. So once you understand that, you can really start to just have a feel when you're doing manual J, when you're doing a design, for what's going to work and what isn't. And some of this stuff, as you probably see, is new territory. There's not a lot of, there's not a lot of data yet on existing homes. We're sort of experimenting as we go with things, but playing it safe and utilizing all the experts that we have access to, such as the manufacturers. They really, of course, know their equipment really well. So the first thing to look at when you're looking at a home is really defining where the thermal and air barriers are. Okay, this looks easy, but it's really not. And so I like this graphic because it shows sort of 3 different scenarios. And without really just getting into them too much, probably the one that's the most tricky is, again, the roof. You either do the whole roof deck from that, here, you do the roof deck all the way down to the eave, or you're doing this thing where you've got an unconditioned space right over here, behind a knee wall kind of thing. But it's a lot of times, we work with builders for a long time, and it's still hard to get this down with some of them, which is that, you've got to have, it's got to be continuous. Paying attention to this detail, making sure that could be a thermal bypass, which could raise the air exchange rate of your home dramatically. And you would not only meet code, but you'd have a different heating and cooling load for an air source heat pump system. So this just shows you 3 different types. It really is important. It's amazing how you can miss things if you're not really looking at it from this sort of conceptual point of view. The most important point really being that the thermal barrier and the air barrier are aligned and they're continuous, no gaps. So it really does kind of matter where the house is built. We do a lot of HERS ratings on the coast, and you just do not want to put a house on the beach without using foam, okay? You don't want to use fiberglass. And so it matters. The wind is much more constant when you're exposed like that, and it can even happen inland. You need to know where you are, and if you're in a high wind area or if you're not. Orientation matters. We know from doing HERS ratings that orientation matters on the HERS rating scale. It can change a HERS rating number from a 55 to a 54 or a 53. And if it's facing south and there's a lot of glazing, yeah, you're going to get a different number than if that glazing is facing the other way. Also, of course, now the code requires solar-ready homes, right? So builders have got to be aware of if their house is not exempt. There's many different exemptions in the code. If you're not facing the right way, you've got to have enough area. You can't have too many obstructions on your roof. But if you are, then the homes need to be solar-ready. So that kind of works together with this to be sort of mindful of the fact that when we do a manual J, we do look at this, because we have the site plans, we know what the orientation is of the house. Equipment locations, very important. Unvented is much more efficient, generally with heat pump systems. I'm going to show you a couple of them in attics. We like them in conditioned attics. If you put them in a cold attic, which I'm going to show you one of those, then you need to be very careful about how you're doing that so as not to generate heat, cause ice dams in the winter, so forth and so on. Generally, as HERS raters, we're telling builders over the years, stop putting heating furnaces in attics. Don't do it in unvented attics because it's stupid for a lot of reasons. Heat a house in the winter with a unit that's up in a cold attic. It's just working against itself, but it's been done for convenience for years. Ventilation is really important. If you're putting a system in an attic, any system, heat pump, anything, you got to make sure it's ventilated or you're going to have ice dams or problems. So this keeps going in the same theme, I like this slide because it's sort of conceptual. But you can put, so it's an air source heat pump system or the indoor air handler. You can put that system, the upper left, which is the cathedralized ceiling, that's your insulated roof deck. The one on the right is actually dropping it below a cold attic, right? And making a soffit down there for the heat pump system. The one on the lower left is, if you can sandwich one between floors, that's great because then it's inside conditioned space that way. And then on the right one, you can actually construct, some type of, in this case, it's a scissor truss plenum that is actually constructed to bring it, so you make like an attic, you make a conditioned space inside the attic for the equipment. And that's often done with furnaces. It's a kind of a can of worms, but with heat pumps, basically the point of this slide is to try to get all the equipment, particularly if it's a ducted system, inside conditioned space. So minimum ventilation requirement is a big consideration in design of air source heat pumps. And in Massachusetts, this is your options in terms of the Mass Code. You can use Energy Star version 3.1, you can use ASHP 62.2, or you can use the formula that's on the bottom there. And that formula on the bottom is really just a more sophisticated version of ASHP 62.2, which is really the minimum. So the point of this slide is, in Massachusetts, the code now requires you have mechanical ventilation for every new home. So we've gotten away from a house has to breathe. Now we're building it tight and we're ventilating right. We know what the minimum ventilation rate is for every single home. We, as HERS raters, when we leave a home, when we test out a new home, we've actually got to set the fan to meet the MVR, the minimum ventilation rate for that home. The MVR is determined by, typically one of those two formulas. Well, the bottom one is probably more common now. And it's really important, so when you're talking about heat loads and cooling loads for a home, a new home, you just want to make sure you got your ventilation set right. So like a colonial would be like, say 80 CFM, a 2,000 square foot colonial. And you want to make sure that you're not over-ventilating, and you want to make sure you're not under-ventilating. Again, that's part of our job. When we leave a home, we got to ensure, and then if it isn't working right, we have to go back to the builder and say, hey, your fan's not working right, you're not ventilating properly, and to get that right. So that's a known, that's a really important component of air source heat pump design, because air exchange is huge, leakage is huge in terms of your heating and cooling loads, right? So what's really nice about this, and what's nice about the Mass Code, is that it's controlled, that we know what it is and we can measure it. It's not some sort of random thing that we're just kind of like, ooh, high, low, or medium. It's not that. We can actually get a real number that we can plug and play with in the software. So, two things about this. To meet the minimum ventilation requirement, most builders are going with the bathroom exhaust fan only as your whole house ventilation. That's on the left. That's in that case, the Panasonic. That runs continuously to meet the 80, I'm going to use 80 for the Colonial. That meets the 80 CFM 24 hours a day requirement for ventilation. The one on the right is the HRV. The difference between the two is the HRV conditions the air that's coming in, preheats it, right? The fan, when every CFM that fan's blowing out, it's ambient air coming in. So when we model these homes, we see that there's a significantly higher heat load when you're just bringing in ambient cold air versus preconditioning with an HRV. So the builders, we just have to know this when we're designing the heat pump system. Most builders are using the fans. I'm going to be nice about this. Most builders are using exhaust fans only because they're only $200, right? Whereas the HRV is going to be $2,000. So they're looking to save on that and just meet the code. So that's an important thing in terms of heat load. Ventilation, again, mass requirement. You got a choice here, and you want to make sure it's accurate. It's actually the CFM that the ASHP standard says it should be for each home. Sometimes it's good to just move air from one room to the next to enhance distribution. And these on the right is a more sophisticated wall fan air mover. And the one on the left is simply, you can just run ducts from one room. You can run a jumper duct from one room to the other one and just pump air. Distribution's important. These are nice little tricks. They're kind of, people don't latch onto them. They're kind of conceptually kind of hard. People get concerned about comfort issues, and that's why you have to really sit down with all the parties and say, is this going to work? And by the way, one of the parties is the realtor, the person selling the home, right? We have builders now who are actually offering a green package. So you've got a convention for the homeowner, the realtor. They're in the model homes. So you've got a model home, which is an all-electric home, and a model home, which is a conventional gas furnace. And when somebody comes to buy the home, they can look at each of those packages and say, I want all electric, I want the green package, or So it's important. I have a meeting next week with a builder, and we're going to do exactly this. We're going to sit down, we're going to go over the whole thing, and his realtor will be there, and she will be saying, this is going to fly, that's not going to fly, my customers aren't going to want that, that will look good or not. And most likely they won't want air wall fans. most don't, but. So the importance of testing and verification. So we use this program called Ecotrope, which is the latest and greatest HERS rating software. And we really like it because it allows you to build a wall. And walls are very important. There's a slide I don't have here, which the Oak Ridge National Lab did a test of different materials and what the true R value is from what the manufacturer is saying and what's really the R value. And typically with fiberglass walls, code calls for R20. So R20, if you're using fiberglass, which says R20 on the label, it's really not. It's really more like R15. So if you got a whole house and it's R15, you're calling it R20, then that's really like good to know, right? Because we're also concerned about oversizing these systems, right? The mantra is don't oversize. And everybody does oversize for the most part. But the one thing you really want to be cognizant of is the true R value of a wall. So with fiberglass, you've got air movement through, it's compromised. The lab will tell you, yes, R20 is really not R20 if it's Dow Corning fiberglass and it's put into a perfect cavity and the cavity's sealed really well. It's still not going to be R20. It's bullshit, right? If it's cellulose, if it's dense packed, that's a more true R value. But you really have to know that, in fact, it's installed right and there's no gaps. Fiberglass is, fiberglass, the wall cavities have to be sealed well. So that we like this because it really gives you a lot of control and we know what we're doing. We can build the wall. You can use any components you want. Where it's brick, you're including the drywall. Even, drywall has an R value. Everything has an R value, except brick. Stone kind of is more of a conductor than a. So ensuring airtightness, again, the HERS rating stuff ties in really well with heat load calcs because when we test the homes, we know how leaky it is. And it's very, very revealing. I'm only showing these slides to show the value of infrared and running an infrared camera with a blower door at the same time. It's really cool. On the upper right, you've got, so the house is depressurized. We're sucking air out of the house. And you can see the purple up on the upper right, that's a tongue and groove style roof. You can see the air just pouring in purple. And you can see, actually that bit right there, that's fiberglass insulation, which that's a gap in that house that was built probably in the 1990s. Tongue and groove is horrible, leaks like hell. If you're gonna ever use it, you wanna put a 4x8 sheets behind it, and nobody ever did that in the past. So, yes, so the blower door allows us to really see what's going on, and sometimes we do it during construction, but mostly it's always done at the end. But it informs us so we can see things ahead of time. It informs a lot of the stuff I'm talking about when I talk about walls. So accurate system sizing for new construction. So obviously manual J and S requirements are not new. They are a code requirement. It's required by code which set limits on oversizing, 40% above so the equipment that you put in is not supposed to be more than 40% above the manual J. I'm just like heating and cooling. However, if you're in a mass save program, and all of our builders are, they want the rebates, then you have to be within 15% of the design load with the equipment that you put in. So that's good to know. So the thing is, there's no real oversight on the sizing. Next slide, I'm going to get into that a little bit, but most HVAC contractors have the guy do it behind the desk who's supplying the equipment. We'll talk about that a little bit. Accurate sizing of air source heat pumps is more critical than with fossil fuel systems. Yes, it is. It's These systems are more precision, they modulate, they're not big beasts that shut off and on, that are grossly oversized, that have an efficiency that doesn't matter. So they do need to be, they're much more sophisticated technology, they need to be done right. The big beasts, the fossil fuel units, cover up a lot of, error. So Manual J, there are a number of different Manual J software packages. We started with CoolCalc, and now we use RightSoft, and we wanted to move towards the most sophisticated software because we want the inputs to be blower door number, accurate information. If you go to CoolCalc or something like that, it's like high, low, medium leakiness for the house, right? So what the heck does that mean, right? So the more sophisticated the software, the better. So what to look for in a Manual J? Room by room load calcs, no padding required, load calculations already have a safety factor built in. That is true, all the software kind of does have a little safety factor built in. Accurate modeling includes air leakage. These are the things I've been talking about. Air leakage areas, orientation, shaded areas, true R values, and of course, window U values and solar heat gain coefficients. And on the U values and the glazing, that's really important to know that area. Of course, you're going to have that area. You're going to know what the area is, particularly facing the south side. If you have a lot of glass on the south side, that's going to make a huge difference in your heating and cooling load. And that area needs to be accurately input into the model. So who should generate the Manual J? So we're definitely saying, if you talk with anybody in the industry who's a professional, they're going to say, and it's in all the literature, if you go on the Green Building Advisor, they're saying, have a third party do your Manual J first. And that could be a HERS rater, could be an engineer, or it could be an energy consultant. There are people who know how to do ACCA accredited Manual Js. But the important thing about having a third party do it is they don't have any skin in the game. They're objective. They're going to just do it. What a builder should do, what we tell builders is, you got a model home that you're building everywhere, right? Like a box colonial. Like one of our builders, they do 100 a year, box colonials. So make sure that you know what the heating load of this house is, and then you can go to the HVAC contractors and say, here's my heating and cooling loads, give me a system for that. If you go straight to the HVAC contractors and you say, hey, here's a house plan, you're going to get an HVAC system that's probably 150 to 200% higher than what you really need. That's just what happens. It's still happening. Really, the best way is for the builder to spend $500 doing a Manual J right up front for each model, get it right, and then get quotes from HVAC. So yeah, the standard approach is the installer or the supply house. They're generated using defaults. There's simple software. There's a variety of different softwares that are used. And so you should verify the inputs. So like I say, the building inspectors aren't really trained to look at a Manual J and verify inputs and that kind of thing. So it's just really, at the very least, if you're having somebody do it from behind who's the HVAC supplier or the HVAC contractor, and that's fine, by the way. Some of them do it really well, and it's fine. Tend to be the bigger HVAC contractors. They'll have their own in-house engineer or whatever. But verifying that it's all, having somebody look at it and say that it's all right. I have one builder. He builds 2 homes a year, but they're 8,000 square foot homes on the Weston Country Club, and they, in that area, and they're like beautiful, gorgeous, super expensive homes. Well, he, of course, makes sure, yes, Tim, I pay $700 to have a Manual J done, because so that I don't depend on any HVAC contractor to give me it. I know, and then I give it to the HVAC contractor. So, and get bids, because you'll get different prices too. And, by the way, if you size the system right, it should be smaller than usual, and therefore cheaper. So this is a quote from Joe Listibrook. HVAC designers committed to institutional oversizing of air conditioning equipment. are committed to institutional oversizing air conditioning equipment. This is in the Green Building Advisor. The average system is sized at 150 to 200% of the requirements of the Manual J. They oversize because they don't know what they will get for a building envelope and to compensate for duct leakage and inappropriate refrigerant charge. If you size according to the Manual J, there is already a fudge factor built in, but most designers add another fudge factor. So in summary of sort of this section, I'm just saying, these are the things, right? That's why it's important to know building enclosure, building your tightness, location of duct systems, and MVR. So here's one of our designs that addresses this situation. We did this a while ago, but basically, so you can see the Manual J. We got the room by room heating and cooling load there for this floor. This is the first floor of a home. And so up on the top, up here, we have a 30K outdoor unit, and then we have a single 9K outdoor unit. So the 30K is your multi-head, and we're concerned about the range of that multi-head being able to meet the low temps, the high temps, the whole full range. So what we did here was we put a 9K unit in the dining living area where people live are going to spend most of their time, so that during the shoulder seasons, during the 40 degree, 50 degree, even 60 degree days, we're going to have a unit that can ramp down really low and handle that low load demand period. So this addresses this. So if I had the same graph up there, the ones we were just looking at, the same type of graph, you would see a multi and a single, and you would see it covering the full range of temperature, average temperature, year-round, summer and winter. So this is another graph that's put out by Mitsubishi, and it shows their specific model numbers and their equipment and their ranges. But basically it shows the full range. If the design temperatures are very different for a low load home versus an average load home, right? So what is a low load home? What is an average load home? Very good questions, right? You got passive house on one hand, right, which is extremely low load, high performance home. You've got mass code, which is one of the most aggressive codes in the country, the most advanced codes, most demanding codes. And then you got older homes, then you got like New Hampshire even, where they're still, and here we're Massachusetts, it's IECC 2015 is the code. And that's pretty advanced. They're still looking at going at the next one, which would be 2018. In New Hampshire, they're still on IECC 2009. So that, for example, the air exchange rate here is 3 air changes. So we know we got that. That reduces the load a lot. And the old one just several years ago, which is still in effect in New Hampshire, is 7 air changes. So that's a huge difference, 3 to 7 air changes. In terms of air leakage, but also, of course, in terms of heating and cooling load. So this is the level to which we have to get down to, right? When we go to do a final design, we're looking at the specs for each piece of equipment, and we're making darn sure that we're going to meet the range necessary for that home and for the individual rooms, depending on how they're going to be using those rooms, right? There's got to be some compromise. Nobody's house is like perfectly comfortable in the laundry room versus the living room versus the bedrooms. Everybody's home has got some cooler spots, right? So you got to be real about it. But this is a starting point where we really want to make sure that we're at least starting with the right equipment, and we're going to be in the right range. So these are, the consequences of improper design are many. However, you're going to have, you're not going to get the COP that you thought you had if you didn't design it right. The system's just got to be, again, the supply meeting the load. You'll have more cycling. If you have cycling, it's going to be a shorter system life. If it falls out of range and it starts cycling too much, could be a problem. Greater temperature fluctuations in the home. And yeah, you could have greater and compromised comfort and humidity levels. And the humidity level thing is the sort of classic air conditioner that's always oversized in New England, right? And so the air conditioner, for air conditioning to work well, it has to work over time to strip out the humidity in the air, right? So you can be in a room that's cool, but it's still uncomfortable because the air conditioner is oversized, it keeps going off and on, you never adjust the humidity, you're only adjusting the temperature. So heat pumps run over a very long period of time, our air conditioning, and they're very good at dropping the humidity level because they're sized properly and they run continuously. So, the key design principles here are, that I'm sort of making is, HERS raters, engineers, installation guides. NEEP is a great resource. Looking at using the NEEP list as your selection point for your, actually the Mass DOER, the ACE, the Alternative Energy Credit, that list is more stringent than NEEP. So those are even more higher performing units. So we kind of, where possible, of course, we're always plugging in the rebates, depending on whether it's an existing home or they're going all electric versus not going all electric. And we refer to the NEEP list and the ACE list, we call ACE, Alternative Energy Credits, the DOER list. And that is a great resource to know you're getting really the best equipment, the equipment that works the best in cold climates. So ensure correct sizing, manual J, S, and D. I didn't talk about D much, but D is distribution, duct design. That's like the most challenging. That's the one that really needs to be have a lot of focus on when you're doing a design with a compact ducted system or any ducted system. Ensure, so single zone equipment whenever possible. Well, I wouldn't say whenever possible. I would say single zone equipment where necessary to make sure you meet the full load. So selected ducted equipment for small spaces. I'm going to get into that a little bit. We definitely use compact ducted systems, and they work really, they're the only solution in some cases for second floor, master suites, that kind of thing. Selected ducted or ductless equipment for larger spaces. Well, yeah, you can use either or. Consider how space will be used for zone design. Obviously, that's where you want to communicate with people who are living in the home, the realtor, the builder. What are their concerns about different rooms and the comfort level in those rooms? And then finally, the homeowner, educating the homeowner. When we design and install a system, we tell our builders, we will come out and spend a half an hour with the homeowner when you sell the house, and we'll show them how to use it. Unfortunately, I think the controllers are kind of user hostile. They could use some help, some improvement there. It's not as super friendly as you would like it. It's written, it's done, the remotes, right? They're done by technical guys who I think never talk to the end user or something, I don't know. But it's like if they could make them more user friendly, that would be a good thing for most homeowners who can barely work a TV controller, right? So that would include me, by the way. So so we spend time with the homeowner, and educating the homeowner is an important part of it. Otherwise, the system may not work. Many of the systems, of course, we're putting in the standard sort of Honeywell thermostat, and all these systems allow you to do that. And for people who don't want to mess around with the more technology. And also there's the remote control, so you can control your room temperatures, all your room temperatures from your phone, which is really a pretty cool thing if you want to go that route. Basic equipment locations and considerations. Ductless units obviously can be used large open spaces. You have to have sufficient clearances top and bottom, and you want to position air units to maximize circulation. I'm going to show you a couple examples of that. So ducted indoor units are very good for small rooms and open spaces. You want to put the ducted system inside conditioned space where possible, and you want to insulate well. If you've got a ducted system in an attic, you want to insulate it, a cold attic, you want to insulate it as best you can. Do's and don'ts for outdoor equipment location. I would say absolutely the most important thing is follow the manufacturer's instructions. Really don't veer from that. A mount on the ground or with sound isolation. We put them all on the ground because they vibrate the house. unless it's a room that's way out of the way, but they can really, especially if it's a 2x4, it's an older home. Leave plenty of space underneath, shield it from snow drifts, protect from roof drip, and consider the aesthetics. Don't mount where water condensate will drip. Outdoor units blow into the intake. Prevailing wind will interfere with the airflow, that's true. Where snow is likely to drift. So this is a bigger box colonial, and you can see that on the first, so this is the first floor, I'm going to show you second floor. So the first floor, this is the builder, we're talking with the builder, this is what they want, this is what makes sense. This actually does seem to be the more common approach, more acceptable to most people, which is first floor, big open concept, most homes are sort of open concept, kitchen, dining connected, and so wall units, right? So these are just all wall units, ductless wall units on the first floor. Second floor, we got two PEADs or two, these are actually medium high static ducted systems for the second floor of this colonial. And it's really necessary because of the layout of this house. A lot of bedrooms, 3 bedrooms, a master suite. And that room, this builder sometimes makes that room go all the way out across the garage, sometimes not only halfway, so we never know. I mean, everyone's different. But so this is kind of bizarro, and it adds a lot of load because there's a lot of area there, wall area. But anyways, this is one of the ways to address that, with 2 units in the attic for supplying heat and cooling to all the second floor rooms, so that they really will be very comfortable. I mean, this is really hitting all the rooms. We've got a supply in the bathroom as well, of course.
Can you go back to the first floor for 1 second?
Sure. This one?
Yeah, the jump jackets in the dining room. Can you just want to talk a little bit about that?
Yeah, so in this one, we actually proposed a jumper duct or a transfer grill to the mudroom, because we don't want to put a unit in that entryway in the mudroom when you walk into the house. So that's a good example of a room that, people walk in, they just want to be transitioned into the house. Maybe it doesn't matter to them, hopefully, that it's super comfortable and warm. So that was the idea there.
There's nothing in the outer room, just the exhaust is sucking air into it?
Exhaust fan running 40 CFM to meet ventilation code. What was the question?
What's the supply? Just
There's no heat supply to that bathroom.
the exhaust is going to be.
Yeah, exactly, and that's something that we look at closely, always. So this is a first floor bathroom. There's no shower in it, and it is a bathroom, or it's a bathroom. It's on the first floor, so we really feel like we've got plenty of supply in the kitchen and the living area. Just keeping that door open. There is a little more exposure there than we like. We tend to do that, like if you've got an exterior wall here and here. So that's a consideration. We know it's going to be a little cooler, but that goes back to the communication with the builder or the homeowner. You say, look, we're going to tell you, we like to do just the bathroom fan with the air filtering in when there's only one wall to the exterior or no walls to the exterior. But in this case, we would highlight that and say, no, you got 2 exterior walls, it may be a little cool in there. Is that okay with you? But that would be a vent fan that runs continuously for whole house ventilation. So it's going to be drawing air into that room. Well, this is a house that was done. This is a box colonial. This is kind of unique. This one here, I don't have the plans, I just have these pictures. But basically, we were the builder told us what he wanted to do. And it's working out really well. I'm actually in touch with the homeowner here. She had a very good winter. She was very comfortable. She said that so basically, I'll just give you the overview of this one. So this is all wall units in a box colonial. Those are 2 24,000 BTU outdoor units. So we got 48,000 BTUs outdoors. And then indoors, we have 6 heads, because each of those units will do 3. And they're placed around the house strategically to move, to circulate air and to satisfy what the builder really did this for us. He said, here's what I want to do. I said, okay, great. So it actually is working really well. He's very smart. So This is the Colonial, that one you see right there. There are two indoor wall units on the first floor. That one has, there's another one diagonally across from that in the dining kitchen area, pointing against this one, only on the right side. So it's circular, so it's all open all the way around, and it's working really well. It's just, there's a counterclockwise air circulation in this home that is created by just two wall units on the first floor, and it's just working really well. The second floor has a limited number of bedrooms. I think there were 3, but those just have the smallest wall units that we could get at the time. At that time, the 6,000 BTU. What I love about Fujitsu, by the way, is we love that 4K indoor head that you guys have, because 4,000 BTUs is just the lowest that we know of for an indoor unit, and that I'd rather use a 4 than a 6 in a smaller bedroom if I'm going to go with a wall unit in a bedroom. But I want to just say too that so the quick little feedback that I have on this is sort of anecdotal. I went over there and talked with the homeowner after that really cold spell we had last winter, right? And I said, how was it? And so she said, it was cold around the perimeter on the first floor. So it's very comfortable otherwise. She keeps the heat at 72. It's very hot. Well, for me, sorry, might not be. A little warm, on the warm side. But she said the perimeter was cold on the first floor just during that period. And we actually have a head in the basement on this. So this is a different, whole other subject is basements, right? If you're gonna put a heat pump water heater in your basement, what are you doing with, how are you gonna do that? And in this case, we have a heat pump water heater in the basement, but we also, instead of insulating the basement ceiling, we decided to insulate the basement walls and bring that whole system inside conditioned space and heat that basement with one single head. So it's a little bit of robbing Peter to pay Paul, because you're using a heat pump, an air source heat pump, to supplement so that the heat pump water heater has enough heat from that room. But it really made sense, and I also wanted to keep that floor warm and have enough heat for the heat pump water heater. And what we know as HERS raters is that a conditioned basement is much better than a cold basement with an insulated ceiling. So the Midwest United States, they don't insulate basement ceilings at all. They insulate basement walls. I don't know, it's some sort of old Yankee thing here where we gotta keep the food cold or something. It's like we insulate our basement ceilings, and I'm not sure why, but we've had a lot of our builders go to insulating basement walls. It makes a lot of sense. You get a better HERS rating, and it's more energy efficient. But basements are a whole other topic, because people who want to go all electric need heat pump water heaters. And where's that heat coming from in the air to preheat the water, right? So that's a big consideration. How are you going to do that, right? So.
Where is this house built? What state?
This is in Salisbury, Mass.
And is there any kind of traditional fuel backup heating system for this? It's getting done.
Yeah. Oh, it is getting done. Southern New England, there's no question. Oh, this is a very cool home in Hopkinton. It's a modular that was brought in from Vermont, and we got on the phone with the homeowner and the manufacturer of the home a couple times, and we came up with a design. And so basically, it's really cool design that the homeowner selected himself, really, with our advice. And so it's basically wall units on the first floor again, and one ducted unit in a cold attic. And so those little red dots those are the supplies. This is a return, and this is the way the thing is. So there's the attic. And so what I said about if you're going to put it in an attic, be careful. This has very, very good attic ventilation, and we're going to bury those ducts in our cellulose. We're going to give them an R60 floor, and we're going to we laid the ductwork as low as possible on the floor, so that when we insulate the attic floor, we can cover the ductwork and add to that R value that's already on the ducts. But there's no other way to do this with this modular home. We had to put that unit in the cold attic. I do want to say that there's one duct that runs, so it does all the second floor, but this is a situation where over here, where's that entryway? Oh, so this mudroom. Yeah, so we have a supply. We have one duct supply going from the attic to the first floor to heat this mudroom. That's part of the duct system on adding to the first floor.
In the exterior wall?
There's a lot of exterior wall. It's a mudroom. There's a small bathroom. The owner said, hey, I'm fine with that. Give me one register in that room and it'll be good. This is a super insulated home too and super airtight. Okay, so I only have a few minutes. So this is that house now, or a month ago. Wall units, those are the registers in the second floor. This is another one. This is one in Boston. This is two ducted units on the second floor, wall units again on the first floor. This is a super insulated house with 1 inch of zip wall foam and zip wall on the exterior, in addition to R20 walls or fiberglass walls. The roof deck is foamed. Very cool. Okay, so this is another one showing the system on the inside, completely inside. There's an attic up there. The roof deck is all spray foamed. That is a one-way cassette that fit between the floor joists. So this is a builder that I have a meeting with next week, and we're going to be going over what he really wants in the green package. We know what these are the elements of a green package. All electric home, ductless or ducted combination, heat pump water heating, HRV, ERV ventilation, induction stovetop, and of course, if you can add solar PV and charging, you're quite cool. You got a all electric, super green home. This is, I'm just showing this, again, builders are moving in the direction of offering these choices to home buyers. So factors that make heat pumps work for new construction: homes that meet the code for the air change, that's number one. Ventilation set to the minimum ventilation requirement. Properly done manual J, S, and D. Informed equipment selection. I think you know what I mean by that now. Design for energy efficiency and comfort. You know, keeping that all in mind, right? Like that's where I'm talking about talking with the builder, talking with people, communicating well, saying, we want to make it energy efficient, but we also need to make it comfortable. Let's keep that in mind from the beginning. And then homeowner education. Somehow it's all getting out there. People are demanding it. Home buyers are more interested in it. Not just young people, older people too, everyone. Yes. Well, the one example we showed you was just transferring air into a front hallway. But no, I mean, you have to be very careful about where you're putting it. You would have to look at what the decibel level of the fan is. The answer is not necessarily, and the reason is because homes are tighter now. We have more control over the ventilation. The reason you need dehumidifiers in older homes is because they leak like hell. And so whatever the humidity level is outside, it's the same inside. So like on a humid day, on a hot, humid day, you're inside of your house. So if we have control, we have tight envelopes, tight building enclosures, and then we're not that concerned about the humidity level fluctuating too much inside the house. So all the systems have what's called a branch box or a distribution box. So you have an big outdoor multi-unit. You then have only 2 lines running into the house to a box, a branch box or a distribution box. From that distribution box, you can have 8 heads. That's a good question. So one of the builders I'm meeting with, 3 years ago, I gave him a proposal for heat pumps, and he said, Tim, they'll never work way out here in the suburbs, because this is all vanilla. People don't want anything, they want all the same, not gonna work. 2 months ago, he called me, he says, Tim, this is coming. People are interested in this now. I want a proposal for it. air source heat pumps for my homes. This is southeastern Massachusetts. I tell him, I says, I told you you would turn, I knew you would turn around on this. I told you 3 years ago. He says, oh, you're right, you did. Are you asking me if it's for a HERS rating or for a heat load calc?
Either.
Yeah, right. Good question. Now you got me cornered. So for a HERS rating, we call it R20. Okay? We got to do everything we can. It's acceptable to the building inspector, and then we're doing everything we can to seal the house and get it to an R20. What I'm saying is, if it's a heat load calc, you may want to think about, really what's in there, because the heat load calc is just supposed to be done right. Nobody's really checking it. You're the professional.